left. Straight ahead is never good at all.
In this problem, we are modeling the ear canal as a tube that is closed at the other end and open at the other end. And we are supposed to calculate the frequencies of the standing waves. So the frequency can be calculated from this relationship, velocity divided by lambda. And we also should note that this is what one full wavelength looks like. Now, we know the velocity of speed in air, which is 343 meters per second. So we only have to find out what are the wavelengths in these different cases. So in first case, we see that this wave is 1/4 of the actual wavelength. So the length of the canal is lambda over 4, which gives us lambda 1 to be 4L. And we can solve from this the resulting frequency, which is F1 V divided by 4L. What about the first overtone? In this case, we see that the wavelength is not quite one full. The full wavelength would look like this. So we have 3/4. So the length of the tube is 3/4 of the full wavelength. And again, the lambda in this case is 4L divided by 3. And frequency of the second case is speed of sound divided by lambda 2, 4L over 3, which is same as 3 times V over 4L, or 3 times frequency 1. As you can see, frequency 1 is in this expression already. In the third case, we have L equaling a little bit over than one full wavelength. In fact, it's one full wavelength and 1/4, so which is 5/4. In this case, the wavelength turns out to be 4/5 of the length of the canal. And again, solving for frequency, we get V divided by 4/5 of an L. And this is same as 5 times V over 4L, which is 5 times the fundamental frequency. Now we are pretty ready to plug in the numbers, so let's calculate the first one. We know that the velocity in air is 343 meters per second, divided by 4 times the length of the canal is 2.5 centimeters, 0.025 meters. This gives us about 3,430 hertz. And in these following cases, we already know that it's 3 times the F1, so 3 times 3,430 gives us about 10,300 hertz. And in the third case, we can calculate this one to be about 17,000 hertz. You can already see the pattern. So the following frequencies are the odd multiples of the fundamental frequency f1. So we could already say that the fourth possible standing wave would have a frequency of 7 times f1. This would be about 24,000 hertz. But the audible range of the human ear is from 20 to 20,000 hertz. So therefore, this is not good for our problem. So our answer constitutes of these 3 frequencies. In this graph we have the sensitivity of the ear. It tells us what is the lowest sound level that the ear can detect at any given frequency. We can see at the ears being the most sensitive around 3 to 4,000 hertz, which coincides our finding from the first part that the first fundamental frequency of the ear canal is 3,400 hertz. And if we keep increasing the frequency, we see that the sensitivity keeps reducing until we get around 10,000 hertz, where the sensitivity flattens out for a while. And this corresponds to the second fundamental frequency that we found. 10,300 hertz was the actual number. So these 2 frequencies are the natural frequencies of the ear canal, dictated by the geometry of the canal. And that is illustrated also in the sensitivity of the ear.
But no one answered me, no one really blind.